part 2 of the diaphragm stretcher project, I'll finish the rest of the parts, do the assembly and try it out in anger. The 10 micrometre foils I'm using are electrolytically plated onto polished drums. Copper that's smelted from ore and melted naturally starts to crystallise and forms three-dimensional grain boundaries as the crystals start to coalesce. Along the boundaries there are line dislocations where some atoms are unable to share the common cloud of electrons in the minimum possible energy state. When copper's work hardened by rolling, bending or stretching, the bulk material undergoes an elastic stretch but then enters a plastic deformation zone as the dislocations at grain boundaries slip and deform, settling into new, stronger and stiffer configurations permanently. First operation is to tidy up the threaded brass rod that pushes the stainless piston. Holding the piston in the 3-jaw does leave a bit of run out, but after a clean up it's negligible.
Nice redefinitions of a bit and negligible there, Neil. Slick.
I'm using a 90-degree 4-flute carbide spotting drill to make the dimple for the threaded rod to press against. I actually made 2 pistons. I also drilled the centre of the dimple in case the threaded rod had a sharp point, which it didn't. A quick sanity check to make sure the piston fits okay. I can mill 2 flats on the body of the stretcher so I can clamp it in a vise. I'm using a 3-flute aluminium geometry YG1 carbide end mill for this. It's got a small corner radius, which will come back to bite me later. When I plonked it into the vise it wouldn't seat properly because I'd forgotten about the radius on the end mill. I went ahead with the next op anyway, but later on I relieved the corner using a hacksaw to make a 45-degree slot.
Nice recovery there, Neil. Oh wait, no. Horrible kludge. Hackers and bodgers, honestly.
The pad on the quill clamp of my indicator's broken, so I get to use my gorgeous Heimer to do the centering. First step's to take a pair of measurements roughly on the centre line. That identifies the centre in the other axis. So I zero that and take another pair of measurements, zero that and then take a final pair, which this time will be pretty accurately on centre. There's more than one way to do things and the Heimer's a joy to use and I don't need a mirror or a camera or a universal joint in my neck. I picked 10 as being a reasonable number of bolts for the bolt circle, but there wasn't any science about it. 11 would have been funnier. So here we go, 10 spots with a centre drill, then 10 nice deep 3.3mm holes. The original depth stopper in my Bridgeport's missing, so I use a spring clamp and lock it in place with a cart twist. One day I'll fix it and fit a quill DRO. One day. I'm setting the depth so I can drill the clearance hole in the ring, which is still superglued heroically to the body. I bet there's an elegant mathematical algorithm to work out the minimum number and distance of axis moves for a 10-hole pattern.
That's probably not it.
With the 10 clearance holes done, I can fire up the blowtorch and warm up the ring so the superglue melts. Folks in meat space, please take note. Not too hot, plenty of ventilation or a remote fed respirator, and don't set fire to your shop. 200 centigrade or 400 Fahrenheit should be enough. Try to keep the heat in the part you're removing so the residue remains on the body or mandrel. A gentle tappy tap tap and we're done. Those are my TIG welding gloves. I didn't feel a thing. Gadget time. I'm using my Tapmatic automatic tapping attachment. It uses internal cones and springs with a cork liner and adjustable clutch. You just have to press down to start it tapping, then it'll drive on till it hits bottom or hits maximum extension. Then it trips the mechanism and runs backward at high speed to extract the tap from the hole. Ten holes done in a jiffy, no drama, no sore fingers. If I can find where I bought it, I'll add a link in the description. For mysterious reasons...
He means fumbling incompetence.
Mysterious reasons, the bit of footage of cutting the 0.1mm ledge on the body's missing, but you can see the faint line where the ridge is. The intersection's just a little above the rest of the face. A quick clean-up of the holes using the mini Noga deburring set, then a chamfer to break the outer edge and trim of the inner edge with another Noga deburrer, and that's the body all done. Just for a change, I'm going to face off the ring and cut the step in reverse. No real reason, just because I fancied trying it. Don't do it if you have a screw-on chuck, obviously. It worked perfectly. The step on the ring's about 50 micrometers tall and it's about 25 micrometers smaller than the matching step in the body. That means the contact area is narrow and just inside the bolt, so hopefully it'll mean I can put serious compressive force on the foil. quick clean up of the holes and it's time for a check of the fit. And I think it'll do. 2 nests of starlings have just fledged, so the racket in the background's about 15 of them yelling at their parents for food. Very noisy here out in the boonies. Back to old school edge finding now, centering an offcut of brass from the scrap bin. I'm drilling 2 clearance holes for M4 screws and tapping an M8 by 0.5, that's near enough 5/16 50 TPI if you're empirically oriented. This is a 7.5mm cobalt stub drill from Drill Service of Hawley. The taps are 3-flute high-speed steel, nothing special. Oh dear, I should have cleaned up those faces. It looks terrible, doesn't it?
Affirmative, Captain.
Now I need to drill and tap the back of the body to take the M4 screws. Nice chaffinch chorus in the background, and there goes my chihuahua barking at the stoggies. Sorry, wood pigeons, for those who aren't from Lincolnshire. No, I don't understand why I'm doing it manually with a spiral point tap either. Rush of blood to the head, mayhaps? It's terribly un-British to ask, but it really helps the channel if you click the like button. Thanks, and extra thanks from Dido. A trial fit and it all looks fine. As my mate Nick would say, job's a good 'un. Next up is to make the knob and threaded adjustment screw from a bit of brass bar. Not from the scrap bin for once. Actual brass bar. Really extravagant. I need to knurl the knob, so I'm just relieving the first part, which will be the thread. I could cut it to size, but a pound to a penny says I'll slip with the knurls and mar the surface.
Did you actually measure that stick out? Looks a bit short to me.
Perceptive as usual, too short. I forgot to allow for that terrible pressure knurl that came out of the same Christmas cracker as the awful janky die stock. Here we go, as they say on the splendid hydraulic press channel. After finishing the knurl, I can turn the shaft to the finished size, cut a step just for prettiness, derag the edges and add champers on each side of the knurl, then make the gutter, thread and the point. As ever with these fine threads, I need to hit the OD accurately when I'm not using a full form tool, so I don't have to bodge the thread tops with the file afterwards. First step with the threads to cut a gutter for the tool to start in, but also to allow the screw to go all the way in without jamming, as you can't get right up to the face with these single point tools. I've turned it to exactly the correct major diameter, which of course is nominal minus 1/8 of the pitch times half the square root of 3 each side, or near enough 0.22 times the pitch smaller than the nominal diameter. For an 8mm by 0.5, that's 7.89mm. If I hit that, I can save a world of pain and measurement just by touching the single point tool so it removes the die chem and then plunging in straight by 5/8 of the theoretical thread height, or about 0.5mm in diameter. Next step's just a tradition for me. I like to use die cam to set the cutting tool so it just scrapes the die when I'm setting the cross slide DRO to 0. I do have a go no go thread gauge in this size, but following the dimensions works really well. With a full form insert I can be much less careful and just check the finished diameter, but that only works properly when cutting towards the chuck, and I almost always cut away from the chuck now, either using an inside wrong way round insert the right way up on the back face of the hole, or an outside wrong way round insert the right way up on the back outside face. Look, it makes sense to me unless I say it out loud, okay? It's like the Joe Pye upside down lathe in reverse method, but on the other side of the axis with the tools the right way up. Safe, simple, stress free. Do not do it if your lathe chuck screws on or is not designed to work in reverse. Bad things will happen. When I finish cutting the threads, I polish them using Kratex or Bright Boy, or if I'm really stuck, like now, I use Gariflex. I follow the manufacturer's recommendations for plunge depth, none of this setting the compound slide malarkey, just go straight in using the cross slide. Recommended steps for these inserts are a bit too fierce. They're designed for high volume production, minimum cycle times and balanced tool life. I take less optimistic cuts. For a 0.275mm radius plunge they say 4 steps, but I prefer doing 6 at 0.06, 0.11, 0.16, 0.21, 0.25, 0.275 in copper and brass, as that gives a reliable result, low tool wear and a good finish. I run the threading at 360 or even 410 RPM and use cutting oil even on brass. Yep, up to 410 RPM for single point threading in M8 by 0.5. Oops, forgot to film turning the tapered tip. I've chucked up a spare M8 by 0.5 122 GHz waveguide combiner that's out of spec to use as a holder for facing off and chamfering the top of the knob. Yeah, I know it's a bit off centre. It lives underneath the device and nobody other than me and the entire YouTube audience will ever know. Now it's time for a bit of analogue semi-freehand curve cutting to make a sort of parabolic fillet on the edge of the ring so it won't crimp or damage the diaphragm. Once more I'm using the excellent Edge Technology Chuck Stop Spider. It's not cheap, but I use it a lot. I'll put a link in the description.
Sorry if I'm being Captain Obvious here, but it would have been nicer to use a form tool.
I used abrasive to blend the facets and give it a bit of a polish. Talking of polish, I stuck the piston into my battery drill to give it a polish with Brasso, and then degreased it with brake cleaner and then acetone, and gave it a faint smear of PTFE lube. The near linear elastic relation between stress and strain becomes more like a parabola in the plastic deformation region. The material doesn't return to the original size and it becomes more rigid and brittle. As this foil's so thin, the crystal boundaries that naturally form in a bulk melt don't quite happen in the same way, but they still exist and can be manipulated by rolling and stretching. I need to stretch the foil well into the initial plastic deformation zone at around 7% strain, and then fix it to a metal ring while it's still under residual elastic tension. I can't show the detail of that or the fine tension adjustment yet because of commercial confidentiality. Patience, dear reader, is a virtue, so I'm told. Never actually tried it. Time for a test. I was useless at getting the foils flat to start with. Now I glue them to a flat ring first, but this is the old method. Here goes. Wish me luck, I'm going to need it. Oh, expletive deleted and invoke a relevant deity.
There are 13 scrap foils in the bin and no good ones yet. Are you feeling lucky?
Well, yes, I think I am. It'll be some time until I can show the next stages and the actual use, so it's back to the low pass filter project. If you're new, I'd really appreciate it if you could subscribe. Try this video next.